Hi everyone! Welcome to part 2 of chapter 8. Last time we learned all about the properties of gases. We learned that pressure was mostly due to molecular collisions, and anything that increased the number of collisions increased the pressure in our gas. We also learned about the volume of gases and the temperature of gases, and we said that the temperature was directly related to the amount of kinetic energy that our gases had. An increase of temperature gave our gases more kinetic energy, which increased the velocity or speed of our molecules. Oftentimes, that also leads to an increase in the number of collisions, which increases the pressure of our gas. So we talked about all of those gas properties. We also learned about kinetic molecular theory, and that was a set of assumptions designed to make thinking about our gases kind of more simple and easier to predict mathematically. We then learned about some simple gas laws, like Boyle's law and Charles' law and Gay-Lussac's law, right? And we learned that the relationships between pressure and volume and temperature, and pressure and temperature could be modeled mathematically. Today, we are going to learn about more gas laws. I know you're excited about that. And we are going to learn how to do more mathematical calculations with these gas properties. So today we're going to learn about the combined gas law. We're going to learn about a set of conditions called STP. And we're going to learn about the ideal gas law and how that ideal gas law can be used to solve for the molar mass of a gas. So lots to do today. Let's get going. So last time we learned all about Boyle's law, Charles' law, and Gay-Lussac's law. And you may have left the last lecture thinking, wow, that's a lot of gas laws. Like, how am I ever going to keep all of those straight? And the good news is, you don't need to. You do need to know that Boyle's law is, the relationship between pressure and volume, and that Charles' law is the relationship between volume and temperature, and that Gay-Lussac's law is the relationship between pressure and temperature, but I don't need you to memorize those individual equations. The reason for that is that we have a better equation, and that's the combined gas law. The combined gas law incorporates all of those gas laws, all three of them, into one super cool equation. So our equation is P1V1 over T1 equals P2V2 over T2, and I like to say, no, it's not related to R2D2, just because it kind of sounds like that. I know it's a little bit silly, but I do want you to know this equation. There are only two equations in this entire chapter that I'm going to have you memorize, and this is one of them. So P1V1 over T1 equals P2V2 over T2. So the way I like to remember it is pink vultures sitting in a tree, or maybe purple vampires sitting in a tree, or you could even think of Professor Verissimo sitting in a tree. However you want to think about that. But somehow or another, remember P1V1 over T1 equals P2V2 over T2. And like I said, the super cool thing about this combined gas law is that all of these gas laws are already wrapped up in here. So let's say you wanted to work on a Boyle's law problem, but you didn't know Boyle's law because I told you, you just have to memorize the combined gas law. Well, in Boyle's law studies the relationship between pressure and volume, and it holds temperature constant. So if we want to hold temperature constant, we just remove it. And there you go. That's Boyle's law. Let's say instead we wanted to hold pressure constant. This would be a Charles' law problem. Or let's say instead you want to hold volume constant so you can solve a Gay-Lussac's law problem. There it is. So whichever variable you want to hold constant, we're just going to remove it from the equation, and that's it. So you have all of those individual gas laws contained in this combined gas law. It's really cool. All right, so this combined gas law incorporates all of the pressure, volume, and temperature relationships for those three gas laws that we studied in the previous lecture. So again, you don't need to know the individual gas laws since you know the combined gas law. And the key here is that the combined gas law is used for studying the effect of changes in our variables. We are going to learn about a couple different types of gas laws, and a lot of times I get the question of, well, how do I know which type of problem I'm solving? Or how do I know which gas law to use? Well, the answer is the combined gas law is used when you have a change in the variables. So if your problem mentions 2 pressures, or 2 volumes, or two temperatures, that will be a combined gas law problem. You'll always see multiple of a certain variable. Okay, so that's how we will recognize it. The other key here is that our combined gas law does not deal with changing the number of moles of a gas. So if you see any mention of moles of a gas, likely you're going to solve an ideal gas law problem, which we haven't learned about yet, but we will shortly, rather than a combined gas law. Combined gas law just deals with pressure, volume, and temperature. And again, you're always going to have a change in the variable. 2 pressures, 2 volumes, 2 temperatures. That's how you'll recognize it as a combined gas law problem. Alrighty, let's go ahead and try this out. So here's an example problem. A balloon is filled with 266 liters of helium gas measured at 38 degrees Celsius and 0.995 atmospheres. What will its volume be when the temperature is lowered to negative 76 degrees Celsius and the pressure is 0.561 atm? So, first off, how do we recognize that this is a combined gas law problem? Well, the key here is that we have multiple temperatures, right? We have 2 temperatures, we have 2 pressures, and we are talking about 2 different volumes. Okay, so since we have 2 different sets of our variables, that's telling us that our conditions are changing. And anytime our conditions are changing, that means we're going to use the combined gas law. So, like always, I like to start out by outlining our variables. So we have our initial volume, 266 liters, our initial pressure, 0.995 atmospheres, and our initial temperature is 38 degrees Celsius. Remember, we cannot use Celsius. We always need to convert our temperatures to Kelvin. So to get from Celsius to Kelvin, we just add 273. So then we're solving for our final volume, we have our final pressure, and then we have our final temperature. Again, it's in Celsius. We need to convert it to Kelvin. All right, so once we have all of our variables kind of lined out, now we're going to go ahead and solve this problem mathematically. Our next step will always be to rearrange our equation, okay? As you can see here, right now, we're trying to solve for V2, but V2 is still next to P2 and being divided by T2, so we need to get it away from those other variables. If you are good at math, go ahead and rearrange this equation the best way you know how. I'm going to show a way right now that works for solving for any variable so that if you're not good at math, if you always follow these steps, you can rearrange these problems simply. Okay, but like I said, if you're good at math, you're welcome to rearrange it a different way. All right, so our first step that I'm always going to want you to do is cross multiply. So we're going to multiply T1 by P2V2 and T2 by P1V1, okay? T1, V1, T2, because that T2 got multiplied up, equals T2, V2, T1, because that T1 got multiplied up by T2, V2. Now, again, I'm trying to solve for V2. So the way that we're going to do that is we're going to divide by anything that's next to V2. Okay? So the things that are next to V2 are P2. So we're going to divide both sides by P2. And then that's done. And we also need to get rid of P1. And then that's done. Okay? So we have V2 by itself now. And so V2 is equal to P1, V1, P2 over P2, V1. So let's go ahead and rewrite that. So it's the same equation. I just kind of flipped it like I've been doing for the past few slides, a few lectures. I like to have the variable that I'm solving for on the left. But if you'd rather have it on the right, you can just leave it the way it is above. So now I can go ahead and fill in all of my variables. So there they are. We can make sure our atmospheres cancel, our kelvins cancel, and we're going to end up with our volume in liters. So there it is. Okay. So I know that math is not everyone's strong suit, and that's okay. But again, always just take our equation, cross multiply, and then divide by what you don't want. If you always do those exact same steps, then you're always going to come up with the right equation. Let's go ahead and give you some practice. This one says a balloon has a volume of 785 milliliters on a fall day when the temperature is 21 degrees Celsius. In the winter, the gas cools to 0 degrees Celsius. What's the new volume of the balloon? Okay, actually, we'll go ahead and go through this one together because I do want to point something out as we're going. So let's look at this. We have two temperatures. We have a volume, and it's talking about we're solving for volume, but do you notice that there's no pressures? There's no pressures at all in this problem. So anytime you see that there are no pressures at all, you can assume that the pressure is being held constant. So when the pressure is being held constant, we're just going to get rid of it in our equation. This becomes a Charles law problem. But we didn't need Charles' law to do this problem. We still just needed the combined gas law. We just need to recognize, oh, hey, no one's talking about pressure. That means pressure is being held constant, so I'm just going to remove it from my equation. So going through and solving this, like I said, we don't have any pressures, so that means our pressures are being held constant. Okay, so instead of our equation looking like this, and I'll go ahead and rearrange this just in a second, our equation will end up looking like this. Okay, so let's think about, okay, we got rid of our pressures. Okay, again, what I would like you to do is just always cross multiply. I think that's always going to be the easiest no matter which variable we're solving for. So if we go ahead and cross multiply here, we're going to get V1 T2, right, because that T2 gets multiplied up, equals V2 T1. And again, we're trying to solve for V2, so we're going to divide both sides by T1. Okay, that gets rid of T1s over there, and that leaves V2 by itself. So V2 is equal to V1 T2 over T1, which is what I'm showing you here. Okay, so if we had not noticed before we rearranged, we would have gotten this one, okay? But again, if you get there and you notice, oh wait, pressure is being held constant, I don't need my pressures, you can just get rid of them either before or after rearranging. It doesn't matter, okay? So whether you recognized it early in the problem or late in the problem, either way, that's okay. So going ahead and talking about the rest of this problem, we had our volume in milliliters, and that's okay, as long as it's fine that our volume comes out in milliliters later. It doesn't specify if we want milliliters or liters here, so we can leave our volume in milliliters just fine. Okay. The only thing that needs to be converted is Celsius has to be converted to Kelvin by adding 273. So once we've got all of this going on, we can go ahead and plug things into our problem now. So V2 is equal to V1 T2 over T1. So we'll plug everything in, and we'll get our answer. And again, our answer is going to come out in milliliters because this one was in milliliters, and we didn't do any conversions to change that. All right, I want you to get some practice on this before you move forward. So complete problems number 15 to 22 on the Chapter 8 lecture worksheet. This will get you a lot of practice on the combined gas law. And you can see all the different variations of when certain variables are being held constant and how that affects how we solve that problem. Okay, so make sure to get a lot of practice, and once you're done, come back and we'll keep going. All right, so now we're going to talk about STP. So STP in chemistry stands for standard temperature and pressure. And so standard temperature and pressure allows us to compare our amounts of gases between different pressures and different temperatures. Remember, I told you that chemistry is a universal language, and because of that, chemistry is done worldwide. And we need to have a set of conditions so that I can compare my results here in California with somebody, say, in Germany or in China, right? We need to be able to compare our results. So this set of conditions, standard temperature and pressure, allows us to do that. So our standard pressure is 1 atmosphere or anything that's equivalent, which means things like 760 millimeters of mercury or 760 torr or 101.3 kilopascals, right? All of that is equivalent, so all of that is a standard pressure, but usually we'll use 1 atms. And then standard temperature is 0 degrees Celsius, but like I've been telling you in gas laws, we can only use Kelvin. So it's more useful to think of it as 273 Kelvin. All right, so a lot of times we will use STP as a set of conditions in solving gas law problems, like this one. So this says a sample of gas occupies 125 milliliters at STP. What is the volume of gas at 65 degrees Celsius and 320 torr? All right, so again, we recognize this as a gas law problem because we're going to have multiple pressures, multiple temperatures, multiple volumes. So here we have a volume and it's asking what's the new volume. In STP, that's telling us a temperature and a pressure, right? Standard temperature and pressure. So we still have a temperature and a temperature and a pressure and a pressure. It just looks a little bit different, okay? But again, since we have multiple temperatures, multiple pressures, multiple volumes, that means that this is a combined gas law problem. So we're going to use P1V1 over T1 equals P2V2 over T2. So let's figure out what we know. So we know that our initial volume is 125 milliliters. We have our initial pressure, remember, was STP. So we needed to figure out what is STP. So STP is 1 ATM, but also anything that it's equivalent to. So do you notice that our second pressure is in torr? So this one is 320 torr. So that's why I use 760 torr here, because our units have to match. If I had used 1 ATM, I wouldn't be able to solve this problem because I need to have my pressure units matching. Okay, so you could have converted 320 torr to ATMs and used it that way. That would have been fine too. Either way, as long as your pressure units match. So you can do 1 ATM and whatever 320 torr is in atmospheres, or you can do 760 torr and 320 torr, either way, okay? And then our initial temperature is our standard temperature, so that's 273 Kelvin. Remember on the last slide, I told you that standard temperature is 0 degrees Celsius, but we can't use 0 degrees Celsius because we can't use Celsius, so we use it as Kelvin. Our T2 is 65 degrees Celsius, so we add 273 and we'll get 338. And again, we're solving for V2. All right, so we need to go ahead and rearrange this equation. So I'll work that out for you. So we have P1 V1 over T1, oops, my apologies, over T1 equals P2 V2 over T2. The first step, like I always say, is to cross multiply. So we'll multiply T1 up there and T2 up there. Okay, so we'll get P1 V1 T2 equals P2 V2 T1. So we're solving here for V2, so we're going to divide by everything that's next to it. We'll divide by P2, so now that's gone, and we'll also divide by T1, so now that's gone. So V2 is by itself. So V2 is equal to P1 V1 T2 over P2 T1. All right, so now we can go ahead and plug things in. So there it is, all of our stuff all plugged in. Make sure all of our units cancel. Oh, and it looks like one of my bars got moved in the wrong spot. So that bar and that one should not be there. My apologies. We are going to get milliliters when we're done with this. Alrighty, I want you to try this one. This one says, what is the volume at STP for a gas that occupies 1.62 liters at 616 torr and 42 degrees Celsius? So just so you know, this will be our initial conditions down here, and these will be our final conditions. Sometimes this problem throws people off because it's kind of written in the reverse order. But if you can see, this is the one we have a volume, a pressure, and a temperature, and we're solving for the volume at STP. So that's our final conditions. So go ahead, try this problem out, and come back when you're ready to see the answer. Alrighty, let's go through this. So the first thing we do is always lay out our variables. So we have our initial volume, our pressure, and our temperature, which we need to convert to Kelvin. And then our second set of conditions, we're solving for our volume, and we have our pressure and our temperature. So next, we'll go ahead and we'll rearrange this equation. So again, first thing I would always do, cross multiply. So we'll get P1 V1 T2 equals P2 V2 T1. And we're solving again for V2, so we'll divide by P2, and those are gone, and T1, so those are gone. So we're solving for V2. So V2 is equal to P1 V1 T2 over P2 T1. So we can plug everything in, and we'll get our answer. You'll notice here that this volume comes out in liters because we had liters for our initial conditions. Whereas in the last problem, we started with milliliters, so it came out in milliliters. Remember, your units are always going to match in these types of problems. Alrighty, let's go ahead and get some more practice. Go ahead and pause here and complete problems number 23 to 30 on the Chapter 8 lecture worksheet. Once you're done, come back and we'll keep going. All right, so we've learned a lot of gas laws so far. We learned about Boyle's law, Charles' law, Gay-Lussac's law, and then we wrapped them all together into the combined gas law. So another law that we haven't talked about with respect to gases is Avogadro's law. You remember, we've already talked about Avogadro a little bit when we talked about Avogadro's number. That was 6.022 times 10 to the 23rd, and that was the number of atoms or molecules that were in a mole. That number was actually named in his honor. His law, his discovery, was that the volume of a gas is directly related to the number of moles of gas when the temperature and pressure are held constant. So far, we haven't had any equations that incorporate the number of moles of gas, but Avogadro does, okay? Avogadro says that if you increase the number of moles, then you're going to increase the volume, okay? So I like to think about this as blowing up a balloon. Let's say we're blowing up a balloon for a party that we have. Every, kind of breath of air that you blow into the balloon, right? If you go right into the balloon, every time you do that, you are blowing more air molecules into the balloon. And what happens? The balloon gets bigger, right? The balloon got bigger because you put more air molecules in there, mostly carbon dioxide because that's what we breathe out, but you're putting more air into that balloon. And as you put more molecules into the balloon, that increases the number of collisions, which kind of increases the pressure inside, which causes the balloon to expand. Okay, so this is saying if pressure and temperature are held constant, as we increase the number of molecules, we're going to increase the volume. So again, I would think about this with respect to blowing up a balloon. So this shows it kind of with a gas cylinder. So as we increase our number of gas molecules, right? So like from here, if we increase our number of gas molecules, you'll see that the pressure went up. If we decrease the number of gas molecules, you'll see that the volume goes down. Oh, sorry, I meant volume goes up and volume goes down. All right? So again, I would just think about it like blowing up a balloon. I think that's the easiest way to kind of relate this. So this number of moles and the volume are directly proportional. If you increase the number of moles, you increase the volume. If you decrease the number of moles, you decrease the volume. So we have this gas law called the ideal gas law that's going to be one single equation that relates all of the properties of a gas. Remember, the combined gas law doesn't take into account the number of moles, but this one does. This one is PV equals nRT, better known as PivNert. And I actually did not make that up. I know I make up a lot of things in this class. Real chemists all use this as PivNert, okay? Not just me saying silly things over here on the screen. Okay, so PV equals nRT is our ideal gas law. So if we know, 3 of these variables, then we can figure out the 4th variable. This is not for changing conditions. Do you see here that we only have one pressure, one volume, one temperature, one number of moles, right? Here, this is for one set of conditions. And if we know 3 of those pieces of information, we can figure out the 4th. Okay, so let's go ahead and figure out all of these variables. So a lot of them we've worked with already. So P stands for pressure, but in this type of gas problem, it must always be in atmospheres. Remember, in the combined gas law, I said that you could use any pressure units as long as they matched. That is not true for the ideal gas law. The ideal gas law must be in atmospheres. Our volume, same kind of thing, must be in liters. Okay, in the combined gas law, I told you milliliters, liters, it doesn't matter as long as your units match. But in the ideal gas law, your volume must be in liters. N is our number of moles. Okay, so it has to be in moles. So if you have grams, you're going to convert it to moles before you can use this equation. And then temperature, just like usual, must be in Kelvin. Okay, our new thing here is R. R is the universal gas constant. Okay, and R will always be the same because it's a constant for any gas. So our ideal gas constant is 0.0821 liters atmospheres over moles Kelvin. This entire thing here is the unit. I know it's a little bit weird. Normally we think about units as like grams or liters, right? But that entire thing is the unit. Liters atmospheres over moles Kelvin, or like I like to remember it, latam molk. Okay, so that's how I remember it, latam molk, because then it has all the units. When you're looking at this constant, it's telling you the units for everything else. So if you ever forget, your volume must be in liters, your pressure must be in atmospheres, number of moles, and then your temperature has to be in Kelvin. So that constant is telling you the units for everything else, which is kind of cool. I will always give you this on quizzes and tests. You're not responsible for memorizing the value of R. You do need to know Pivnert, but you're going to use it so much in these practice problems that you're going to kind of accidentally memorize it. But I'll give you the value of R always. Okay. All right, let's try this one. This is an ideal gas law problem. This says how many moles of helium are contained in a 0.900 liter container at 30 degrees Celsius and 0.8 ATMs. So again, a common question I get asked in the gas laws chapter is, how do I know which type of problem I'm solving? Well, do you see here we only have one temperature, one pressure, one volume? That means that we are solving an ideal gas law problem because our conditions are not changing. Okay, that's how you're going to know the difference. So if you only have one pressure, one volume, one temperature, that's an ideal gas law problem. Again, we're also solving for moles here, and the combined gas law doesn't tell us anything about moles. So that's another tip-off. All right, let's go ahead and solve this. So the first thing I always like to do is figure out what my variables are. So I know my pressure, my volume, and my temperature, and again, must convert temperature to Kelvin, just like usual. Okay. When we are doing these problems, we also need to rearrange it just like we've done before. So if we have PV equals nRT, the nice thing here is we don't need to cross multiply because there's nothing in the denominator. So we just need to get N by itself. So to do that, we're going to divide both sides by R. So then that's gone. And T. So that's gone. So we have N is equal to PV over RT. So we can go ahead and plug stuff in. So we have pressure and volume divided by R and T. Okay, so when you plug this in, you can make sure all of your units cancel and you're left with moles, which is what we're trying to find. All right, I want you to try this one. This says what volume will be occupied by 0.393 moles of nitrogen at 0.971 atmospheres and 24 degrees Celsius. So go ahead and try this. Figure out what all of your variables are, rearrange your equation, plug things in, and see what you get. Once you're done, come back and we'll go over it. Alrighty. So, things that we know. We know our pressure, we know our number of moles, and we know our temperature that we've converted to Kelvin. Okay? Our next step will be to rearrange our equation. So we have PV equals nRT. Here we're solving for volume, so we'll go ahead and divide both sides by pressure so that we get volume by itself. So we get volume is equal to nRT over P. So we can go ahead and plug everything in. So there's nRT over P. We'll make sure all of our units cancel, and we're left with liters, which is what we were trying to find. All right, let's go ahead and practice this. Go ahead and complete problems number 31 to 36 on the Chapter 8 lecture worksheet. Once you're done, come back and we have a little bit more to go in Chapter 8. Alrighty, so our last type of problem that we're going to solve today is using the ideal gas law to solve for the molar mass of a gas. This is really neat because let's say we had some mystery gas at some pressure and volume and temperature, and we were able to measure all of those conditions. And let's say we knew the mass of our gas, but we wanted to know the molar mass to identify it. Well, we can use this alternate form of the ideal gas law to solve for the molar mass of our gas and then determine its identity. So that's pretty cool. So here's our ideal gas law, just like normal, PV equals nRT. And so we can actually rearrange kind of our definition of molar mass to solve for the number of moles. So normally molar mass, or capital M, is grams per mole. Or in this case, since we're using N as the number of moles, we can say it's grams per N, essentially. So if we were to rearrange this, we can solve for N and say that, okay, N is our mass in grams divided by our molar mass. So if we took this grams over M and we plug it in here for N, we can get that PV equals grams times RT over our molar mass. And so we can use this new version of our ideal gas law to solve for the molar mass of a gas. You do not need to memorize this equation. I do want you to know Pivnert, right? That one I want you to know. So the two equations in this chapter that you're responsible for knowing are the combined gas law, P1V1 over T1 equals P2V2 over T2, and the ideal gas law, which is Pivnert. I will give you anything else, like this one, to solve for the molar mass of a gas. You just need to know how to use it. So let's go ahead and try an example problem. This says a 0.210 gram gas sample has a pressure of 432 torr in a 333 milliliter container at 23 degrees Celsius. What is the molar mass of the gas? So again, I think this is pretty cool. We know the pressure, we know the volume, and we know the temperature, and we also know the mass of this thing. So we can use those pieces of information to figure out the molar mass, and we could then use that molar mass to identify our gas, which is cool. So there's our equation, PV equals GRT over M. So just like normal, we're going to figure out all our variables. We have our pressure, our volume, our temperature, and the mass. Remember, this is a type of our ideal gas law. So our pressure can't be in torr. We need to convert our pressure to atmospheres. And the way we do that is we divide by 760. So remember, 432 torr, we could make a quick little conversion train track, and we say there's 760 torr in 1 ATM. So that's why I'm dividing by 760 there. Okay, so that will get us our pressure in atmospheres. We need to then convert our milliliters to liters. Remember, there are 1,000 milliliters in 1 liter. So if we have 333 milliliters, we can use that conversion factor to convert milliliters into liters by dividing by 1,000. So that's how we got our volume in liters there. Then we have our temperature, right? Again, to convert our temperature, we added 273. So that's how we got 296 Kelvin. And then our mass, we don't need to do anything to. We can just leave that in grams. All right. So then we need to convert, or we need to rearrange our equation. PV equals GRT over M. So the first thing that we should do is kind of cross multiply again. So that mass is going to get multiplied by pressure times volume. So we'll get pressure, volume, and M, which is our molar mass, equals GRT. Okay, then we can divide both sides by what we don't need. So here we want to get rid of pressure on that side, so it's gone, and volume as well, so it's gone, which leaves molar mass by itself. So that's how we're getting molar mass is equal to GRT over PV. Then we can go ahead and plug all of that in. So we have our grams, our R value, and our temperature divided by our pressure and our volume. So we make sure all of our units cancel. We're left with grams and moles, which gives us our molar mass in grams per mole. So again, we could then use that molar mass to go through and identify our gas. All right, your turn. This says calculate the molar mass of an unknown gas if 0.768 grams occupies a volume of 754 milliliters at 30 degrees Celsius and 342 torr. So when you're doing this problem, make sure to outline your variables, convert all of them into the desired units, rearrange your equation, and then plug things in. So go ahead, pause here, try that out, and then come back when you're ready to see the answer. Alrighty, let's go ahead and try this out. So again, we're calculating the molar mass just like the previous problem. So the first thing I would recommend, figure out all of our variables. So there they are. So we have our pressure is in 342 torr. Again, to convert torr to atmospheres, we divide by 760. So there we get 0.450 atmospheres. And then we'll take our volume, 754 milliliters, divide by 1,000, that will get us our liters. So I'll just put these here. So this one we're dividing by 760, and this one we're dividing by 1,000, okay? And then we need to convert our temperature to Kelvin, and we do that by adding 273. And then we don't need to do anything to our mass. Our next step will be to rearrange our equation. Again, I would start by cross multiplying. So we'll multiply that mass, that molar mass times pressure and volume. So we get PVM equals GRT, okay? So now to get our molar mass by itself, we're going to divide both sides by pressure and by volume. And that will give us molar mass by itself on that side. So molar mass is equal to GRT over PV. So now we can plug everything in. Make sure our units cancel, and we're left with grams per mole. So that will give us our answer of 56.3 grams per mole. Alrighty, so this corresponds to problems number 37 to 39 on the Chapter 8 lecture worksheet. But you'll notice there's actually a lot more problems on this lecture worksheet. The reason for that is that people get tripped up on the calculations, and a lot of it is just trying to figure out what type of problem you're solving, right? And can you leave the units in torr, or do you need to convert them to ATMs, right? And all of that kind of stuff. So I've given you a bunch of additional problems on this lecture worksheet to make sure that you get enough practice with our gas law problems so that you feel really, really confident in that you know how to do all of the problems in this chapter. So 37 to 39 are specifically on what we just covered, but 40 to 68 are just kind of a mixture of all the gas law problems that we've talked about. So the combined gas law is all mixed in with the ideal gas law, so you can get the experience of trying to figure out which type of gas law problem am I solving. So I'm trying to help you out there. All right, this is actually the end of Chapter 8. So today we did essentially a lot of math, right? We learned about the combined gas law and how we don't then need to individually know Boyle's law, Charles' law, and Gay-Lussac's law. So I think that's a lot easier because you're just memorizing one equation instead of three. Then we talked about STP, that standard set of conditions. So we had that standard temperature, which is 0 degrees Celsius or 273 Kelvin, and our standard pressure is 1 atmosphere or anything that's equal to. And that allows us to kind of compare our calculations across different locations. We also learned about the ideal gas law, and that is when we have just one set of conditions, one pressure, one volume, one temperature, and we're trying to figure out one of the other variables. We then wrapped up today's lecture by talking about how to use the ideal gas law to calculate the molar mass of a gas. So we did a lot of calculations today, but hopefully they're straightforward enough that with some practice, you'll feel really confident about them. So make sure to do lots of practice problems. Like I said, I've provided you a ton of them on this lecture worksheet, so I really do hope that helps. If you get stuck, make sure to reach out, and I'm more than happy to kind of walk you through it and troubleshoot where you're getting stuck. Otherwise, just keep working hard, do lots of practice problems, and I will talk to you guys next time.